Okay, all right, so let's continue. And like I said, what we're going to do is we're going to see that a quantum spin is going to behave exactly the same. So we're going to have a quantum spin in a classical magnetic field. And what we're going to do is we're going to see that the dynamics are the same as the classical spin. Okay? So we start with a Hamiltonian. So this is minus mu dot B. And we're going to choose our field to be in the z direction. So it's going to be some B0 in the z direction. And this is, again, this is a classical field. And so we get minus gamma LZ. This is our angular momentum operator. That's how we go from classical to quantum. We put hats on things and they become quantum. Okay, so there's LZ, B naught. But if we did our quantization properly, then this is our Hamiltonian, and our eigenenergies are going to be minus gamma H bar B0 M, where M are quantum numbers and they go from I minus 1, so on and so on, all the way to minus I. These are eigenenergies. And these are eigenvalues. Eigenvalues of LZ. Yeah. And with this Hamiltonian, we can just write the equations of motion. And equation of motion for some operator O, we know that O dot equals I over H bar, H O plus the explicit time derivative of O. Okay, so now we're going to write this equation for our angular momentum operator, and from that we'll get the dynamics, and we'll see basically that we get the same Larmor precession as we did for the classical spin. So let me write this explicitly.
What is I when you say M goes from I to minus I?
I is a number. So in your second course of quantum mechanics, or maybe in the first one, you quantized the angular momentum and you had a spin, right? And a spin has some number n. So a spin half will have plus minus half, right? A spin 1 will have minus 1, 0, and plus 1. Okay, yes. The spin, spin 5 halves will be minus 5 halves, and so on and so on. Okay, so that's exactly what you saw in quantum mechanics course. Okay, so now we're going to apply this equation to our spin. So apply to our spin. And I'm just going to write the equation for the x component of our angular momentum, which just equals mu dot x, which if we now just plug into the equation of motion, we'll just get I gamma b naught over h bar LZ commutator with Lx. And the commutation relations for the angular momentum operators are cyclic, if you remember. So Li Lj or I h bar epsilon I jk Lk. So if we plug that into here, we get gamma b naught Ly. So Lx dot is going to equal gamma b naught Ly. And if we write this in vector form, so mu vector dot, and hang on, let me put, so this mu vector hat dot, so it's our operator, but it's the vector, so it's the three components, x, y, and z, and it's the time derivative. It will just be mu vector operator cross gamma b. And if we now look at the expectation values, then we just get mu dot equals the average of mu, and to put hat for operator here, cross gamma b. And these are the dynamics that we got for a classical magnetic moment in a classical magnetic field. You can see that for a quantum spin, or an ensemble of non-interacting quantum spins, so call this non-interacting, the dynamics are the same. Okay? So dynamics are the same as classical. Now, we can go a step further even, and let's assume that our spin is a spin half. Okay, so the equation that we just wrote says that for a quantum spin, if you measure the average magnetization, you get the same results as the average magnetization of a classical magnetic moment. Okay? But now, let's take spin half. In the case of a spin half, if you remember, a spin half is basically a two-level system. And for a spin half, you describe the state, the quantum state of the spin half on what? How do you describe it? On the
Bloch sphere.
On the Bloch sphere, right? Exactly. Z. So this is Bloch sphere. And this is psi for our spin half. And note this, I don't know if it's strange, I don't know if it's surprising, maybe it's not surprising, equivalent, that if I look at a magnetic moment, and I look at its magnetization of classical magnetic moment, then it can also be described on our x, y, and z axis, and the direction of the magnetization kind of corresponds to the direction of the Bloch sphere. Okay, basically, the magnetization is isomorphic to this two-level system. Okay? So a spin half, a magnetic spin half, will have the same dynamics as a classical magnetic moment. And sometimes you can get confused and think about the Bloch sphere description as a magnetic direction, and in this case you can actually map it, but it's not. It's a different description. This is a quantum state, psi, parametrized by theta and phi, and this is your magnetization. Okay? But they do correspond to each other, and it's a quite nice correspondence as long as you don't get them confused. But what it does tell us, and this is the important thing, that any two-level system, and it doesn't need to be a magnetic spin, but any two-level system will show the same dynamics. So all the dynamics that I was talking about till now, with this classical magnetic moment, you can take this intuition and apply a lot of it into a single qubit that's not interacting with any other qubits. And the intuition that you got for this magnetization of this magnetic moment, you can apply to the dynamics on a Bloch sphere of a single qubit. You got to be careful here. And the qubits need to be, non-interacting, but you can definitely play around with this correspondence to get some intuition. Okay? And to make it a bit more explicit, what I'm going to do now, we're going to look at a two-level system. We're going to look at an electric dipole. So we talked until now about a magnetic moment, and we saw that a magnetic moment has dynamics like any two-level system, basically. And we're going to take a quantum two-level system, which is an electric dipole, and we're going to look at those dynamics. Okay? And we're going to see how we get Rabi oscillations by applying an electromagnetic field onto this electric dipole. Okay, so we start off with an electric dipole. So our electric dipole is going to be described by two levels. It's basically a qubit, 0 and 1, with some frequency difference h bar omega q for qubit. The Hamiltonian of this qubit is h bar omega q over 2 sigma z. And it's an electric dipole, so it's going to have an interaction with an electric field. So the interaction Hamiltonian is minus d dot e perpendicular 0. I'll explain what I wrote now. Okay, so this is the interaction Hamiltonian. Oh, sorry, I forgot to write that. The derivation that I'm doing now is taken from the Serge Haroche book. The one that I gave you at the beginning of the semester, called Exploring the Quantum. It's taken from page 145. This book in general is highly recommended reading. Please read chapters 1, 2, and 3. Chapter 3 mostly regards what we're doing here, interactions of atoms and electromagnetic fields. Chapter 2 is very instructive to learn about quantum measurements and the environment and things like that. So please read that book. It's or at least those 3 chapters. They'll be very instructive and enlightening for you. Okay, so back to this.
What chapters again?
Sorry?
What chapters again did you recommend it?
Oh, chapters 1, 2, 3.
Thank you.
Page 145 is chapter 3. All right. Okay, so the interaction Hamiltonian, this is our dipole, and this is our electric field. Now we're taking the transverse component of the electric field. And I wrote here 0 because we're assuming that our dipole is tiny with respect to the wavelength. So what we're doing here, we're taking something that is called the dipole approximation. Okay? It's a convenient approximation that is done when you take a field and some distribution of charges. But if the wavelength is much, much longer and everything is tiny, then you can sum up over the charge distribution and get this dipole moment, which has a certain direction in space, but it's tiny. So you can assume that it sits there at some point. So the wavelength is much longer. Okay, and it sits there at 0. This is why I wrote E of 0. And the transverse component basically comes from, if you look at the Maxwell equations, you separate them out. And if you have no charge distribution in space, so you have empty space, then all you have basically are these transverse components. Okay, you're left with the normal modes, the transverse components, which later translate into harmonic oscillators. We'll see that later. Okay, so this is why I put the transverse part here. We're not going to do the rigorous derivation of this. This is for a different course. But now I'm going to write the electric field. So this is an electric field if you were to just apply some field in free space. And this is what we're thinking of. So some dipole moment, and then you take a laser or something and you shine at it. That's basically an electric field that you're applying on this dipole moment. Okay? And our electric field is still classical, so we're still talking about a classical field. And so this can be written as I epsilon d. This is the amplitude of our drive. Amplitude of drive. Then we have epsilon d here. This is a different epsilon. Okay. This is a unit vector. This is the polarization of our driving field. So we're driving some linearly polarized field. So think of a laser beam. E to the minus I omega drive t. So our field is going to be at some frequency omega drive, and it's going to have some phase e to the minus I phi plus phi naught. The separation into two different phases is just for convenience later, so we'll get a Rabi frequency that is real. Okay, so we can set Rabi frequency to be real. And then basically the conjugate part, so ED star, e to the I omega drive t, e to the I phi plus phi naught, like that. Okay. So this is our electric field, and our dipole is going to be the following operator. Can you see down here in the board? Anyone? Yes? No?
Yes.
Yes. Okay, good. So our dipole operator is just going to be Q, some effective charge, okay? And then we have 0, R. R is the position of our dipole moment, okay, in space. 1. So the overlap of the 1 state and the 0 state with our R, sigma minus plus 1 R 0 sigma plus. And what this operator does, you can see this is sigma minus sigma plus. This is exactly what describes the flipping of this two-level system, of this electric dipole, due to the interaction with a field. And if you calculate this, maybe I'll write it on a different board, I don't know if you can see. So if you calculate Q 0 R 1, you will get some number which we will call D in some direction, basically in the dipole direction. Okay? We've defined here the direction of the dipole with respect to the dipole operator. Okay? So the dipole now, our dipole moment Q, has some direction in space. So now what we're going to do is we're going to go into the rotating frame. And we're basically doing similar things, basically the same things that we did with our magnetic moment. Okay, so we're going to go into the rotating frame. And to go into the rotating frame, we're going to apply the following transformation. E to the I H bar omega drive sigma z t. Okay, so we're going to go, this is the transformation that's going to take us into the frame that is rotating at the drive frequency. Okay? We have a drive frequency. This drive is not a rotating drive. It's a linear drive, but a linear drive, you can think of a combination of a rotating field and another field that's rotating in the other direction. Okay? And then you get some polarization in some direction in space. So we're going to go into the field, into the frame that's rotating at the drive frequency. And then we get the following result. So H prime, this is our Hamiltonian in this rotating frame. And we're just going to do U. We're going to apply U onto HQ plus HI. So this is our Hamiltonian for the dipole moment. The electric dipole plus the interaction with the electric field. Then we're going to have U dagger plus I H bar U dot. Those who don't remember, this is how you transform a Hamiltonian. If you have a Hamiltonian in the new frame, it's just going to be U HU plus the explicit time dependence. A lot of the time this drops because U is time independent. But in our case, we're going to the rotating frame and we have a time dependence in U. Okay, so now we're going to apply this. And I won't do the explicit math, but I am going to point out the important things so it is easy for you to do it at home. The first thing that you note is that this transformation is chosen explicitly. Okay, you can see the form of this if you just look at this term. If you calculate this from this, you can see that it cancels part of this Hamiltonian. Okay, so if I write the dipole Hamiltonian, if I split it into two parts that look like this, h bar omega drive over 2 sigma z plus h bar delta over 2 sigma z, where delta is just going to be omega drive minus omega q. Sorry, I've defined it the other way around. Omega q minus omega drive. Now, just to remind you here, I'll write it down here. I'll write it up here, so you can follow. Remember, HQ was h bar omega q over 2 sigma z. Okay, so this thing I've rewritten like this. It's basically omega d plus the difference of omega q and omega d. So this thing is exactly that thing. And this is delta here. But it's written this way because you can take the derivative of this thing in your head. So u dot, all this drops down, times u itself, so the exponentials go away. Then you get h bar and I. What you can see is that these two terms now, what happens to them? They cancel out. So this part is going to drop with that part. And then our Hamiltonian is just going to be left with the detuning of our drive from omega q. Okay, omega q is the equivalent of the Larmor frequency for the magnetic spin. Okay? So these two are going to cancel out in the rotating frame, and we're just going to be left with the detuning. If you remember our quantum spin, it's kind of the same. Okay, you detune and you get this extra rotation around the z-axis. Okay, so this is where it comes from in this. The second thing that we're going to do is we're going to drop 2 omega d terms. Okay? After you do this transformation, you're going to be left with two types of terms. Ones that are static. Remember, in the magnetic moment case, we went into the rotating field, so this was our magnetic moment. We went into the rotating field and it was static because we were rotating with it. Here we have a linear drive. So one component of this linear drive is rotating at omega d, and that's going to be static. But there's a counter-rotating term, and that one's going to be rotating at 2 omega d. And what we're going to do is we're going to assume that we're looking at time scales which are longer than that frequency. So that thing will average out, and we're going to be dropping these terms. Okay? So we do this because basically we took a linear field. And now we're just taking the rotating part of that linear field. So effectively, we're treating it effectively as if it was a rotating field. And if you take these two into account, then this becomes pretty much algebra, and then you end up with h bar over 2 delta delta omega Rabi e to the I phi and omega Rabi e to the minus I phi, where omega Rabi is 2d over h bar epsilon q star epsilon d e to the I phi naught large epsilon d. So just like in the magnetic moment case, we have our spin. It gets extra phase rotation from the detuning. Sorry, I'm missing a minus sign here. And when we apply a field, we get a rotation at a Rabi frequency, omega r, and this Rabi frequency is also proportional to the amplitude of the field, just like it was in the magnetic moment case. You can take phi naught to be 0 and get a real Rabi frequency. That makes this simpler. It's proportional also to the magnetic moment and to the direction in space of the field. Okay, so now let's look a little bit at how these dynamics, what these dynamics look like. And we'll see that they're basically the same as our quantum spin, but we'll look at them just slightly differently. Okay? And then I'll stop for questions. So what we're going to do now is we're going to take phi to be 0, basically for simplicity. And that makes our Hamiltonian h bar over 2 delta omega Rabi minus delta. So this is now a pretty simple Hamiltonian which you've solved several times, sort of. And the solution, you get energy eigenstates of this Hamiltonian. They look like this. It's plus minus h bar over 2 square root of delta squared plus omega Rabi squared. So these are our energy solutions. And if we draw this, so what I'm drawing now is the energy as function of delta, the detuning. So if we're on resonance, delta equals 0, we basically get two states which are separated by the Rabi frequency. This is exactly the same as with the quantum spin. And you can think of it as a new low frequency qubit. So you started off with this qubit with omega q, and now you're driving it. This Rabi drive is basically coupling. So you have 0 and 1 here. And this Rabi drive is basically coupling 0 and 1. So it's bringing them, naively it's bringing them to the same energy. But it's also doing it at a certain frequency. That energy is causing a splitting. And this is the splitting at 0 energy. And now if you start detuning your drive, you will get this parabola over here. Like that. So this difference over here, this is omega r. So on resonance, you have this new two-level system, which is separated by omega r. Now if we take this omega r to be 0, so basically almost no field, then your solution will look something like this. So these are the asymptotes for the solution of a 0 driving amplitude. And these two energy solutions, we can now, if we now go back to rapid adiabatic passage, we can look at the rapid adiabatic passage problem here in this quantum version. Okay, so I'm trying to connect things that we did classically to what we're doing quantumly. If we're highly detuned and our magnetization starts somewhere over here, okay, if we go really slowly, we're going to stay on this branch and our magnetization is going to flip. Right? Remember, this solution corresponds to this, and this solution corresponds to that. If we go really fast, we just stay on the same branch. Okay, so our magnetization is just going to stay like that. But if we go slow, adiabatically, then basically we're going from one state to the other state. This is the quantum equivalent of the rapid adiabatic passage. And you can look at the calculation for this, and this is what is called a Landau-Zener transition. And if you do the calculation or look on Wikipedia, you can see that the probability of a jump so to jump from one state to the other equals e to the minus 2 pi ni, where ni is omega r over 2 squared 1 over delta dot. So if you go really, really slowly, you're just going to stay here. This is the rapid adiabatic passage. And if you go fast, you're just going to stay over here. Okay, so what did we see till now in this quantum version, in this quantum dipole? We saw two things that we saw in the classical case. We saw that we have our, if I go back to this board, we have our electric dipole. It has an interaction with an electric field. We're driving it with this field at omega d, the driving frequency. This driving frequency causes Rabi oscillations. You can see over here on this Hamiltonian. So we're getting Rabi oscillations. So we start at a certain state. We can apply our field for pi over omega Rabi and we will flip. What happens if we now apply it for half the time?
We get a plus state.
We get a plus state, right? If we now apply and do half a rotation, for the magnetic moment, for the classical case, it just means that we're physically rotating the magnetization. And the magnetization is now in plane and rotating at the Larmor frequency and so on. It's a classical magnetization. For the quantum state, we're going from, let's say, 0 to the plus state. Or if we flip the phase, we go from 0 to the minus state. Or we can do a pi. Or by playing with the phases, we can rotate around any axis that we want. Okay? So we're getting the same full control over the magnetization that we saw for the classical case. The same ideas, the same equations give us full control over a qubit. How do we get Z control over the qubit? In this case, the simplest way to get Z control.
Change the electric field or add to the electric
It's
field?
It's hard. No, the electric field is an AC field. We don't have a DC field. There is no DC field. This electric dipole, omega q, is given simply by the dipole operator. Okay, simply by the charges. Okay, so there's no equivalent of the DC field here in that sense.
We change the delta.
We can change delta and get some rotations like that, yeah. We can change the phases on the drives like, who said it in the previous, I think he's gone now, but he was in the previous hour. Daniel said you can change, you can do like an X rotation and a Y rotation or things like that and play with the phases. Or you can do what Noga did last time and play with a clock. Okay? So you get a Z rotation that way. So we see that we can get full control over a two-level system, over a non-interacting two-level system, whether it's a classical magnetic moment or an electrical quantum spin, or an electrical dipole, or a quantum spin. Okay? And with that, I think we have sufficient background to start explaining what an NMR setup looks like, basically an ensemble of spins, and how you build an experiment that can do some form of quantum computation. So this is going to be our next thing. We're going to be talking about an NMR quantum computer. You can ask questions while I'm erasing the board here. Okay, so what does an NMR setup look like? So the idea with NMR, I'm going to show you what an NMR setup looks like. After I show you what an NMR setup looks like and describe the general idea, we're going to have a discussion about real experiments, so coherence times, decay rates, and things like that. And then we'll actually construct how you do computation in such a setup. Okay, so an NMR setup would look something like this. Some of you might have done an NMR experiment. So you have some ampule with a solution, and this solution would have basically nuclear magnetic moments. Okay, this nuclear magnetic resonance. Okay, so we're going to have these nuclear spins. So we have a big ensemble of nuclear spins, and we apply a big field to them. So these are coils. This applies a field. This is going to be our Z field, our large Z field. And we're going to be applying RF pulses. Okay? These fields are not going to be rotating fields, linear fields, but we already understand that that's going to be the same. So we're going to have another coil, for example, wrapping this solution. This coil is going to be grounded over here. And it's going to be coupled. So this is a capacitor. And we're going to be sending in RF pulses. And the setup looks like this. I'm going to draw it, and then I'll explain what it looks like. So what I'm drawing here, this is a directional coupler. You will understand soon what its role is. This triangle over here is an amplifier, just to amplify signals. This is a mixer. I will explain what it does in a moment. This is another amplifier, another mixer, possibly another amplifier, and a computer. This is a computer. This here is an AWG, arbitrary waveform generator. This is going to be responsible for pulses. So it can do pulses. And over here we're going to have a constant sine wave something that is called a local oscillator. And this local oscillator is going to be split two ways. It's going to be split once going into here, and two, it's going to be split into the mixer. So this is the setup. And now let me explain what is going on here and how you generate pulses. Stop me for questions, okay, if you need. But what's going on here is this LO is called a local oscillator. Basically, you want to set it somewhere around where you think the resonance frequency of your nuclear magnetic moments are going to be. So this is basically somewhere around the Larmor frequency, according to the B field. This thing is going to be split up. It goes into a mixer. To give it a reference, what a mixer does, so a mixer will have some LO port. It will have some I and Q ports, but it doesn't have to have I and Q ports. It can just have, let's say, call it an I port, and some output port called RF. And we can have I and Q, but Q, let's keep it 0. And what the mixer will do, the RF port, the output of the RF port is going to be I as function of t cosine omega LO t plus some phase, right, cosine, plus q of t sine omega LO t plus phi. And if you look at this equation, if you modulate I at some frequency, then you're basically modulating the amplitude of this drive frequency. So if this LO is giving you some constant drive, this is omega Larmor, so it's giving you some this. If you start modulating by I, you will get, suppose that you're modulating I by some omega frequency, then you will get these sidebands that suddenly appear. If you're doing it very slow, suppose that I is 0 and Q is 0, then you get nothing. But now if you do it really slow, you ramp I very slowly up and then very slowly down. Basically what you're doing, if it's much slower than this, is you're turning this on and then turning it off. So this mixer is acting like a switch. If you do it really slow, then it's acting like a switch for frequencies at what you think is the Larmor frequency. If you modulate it faster, you can get sideband, so you can also apply at slightly higher frequencies pulses. But basically, by modulating this, you can apply whatever pulses you want in time, okay? As long as you're within some band. And this band is basically set by this machine, which you can program some voltage as function of time coming out of this. And this voltage coming out of time goes into this port, which modulate this. So the role of all of this thing, and afterwards you want to amplify it maybe. So the role of this thing is to create whatever arbitrary pulse we want. Note that we can control the phase also by controlling the phase of this thing, of I. So the role of this is to give us arbitrary control over the field that we're sending to our system. Oh, we're kind of out of time, so let me just quickly finish and I'll recap at the beginning of the next lesson. This thing goes into this coupler. I'll explain this next lesson what happens, but the idea is that you want the energy to go into this coil, then you want the signal to be reflected. This coil also acts basically as an oscillator. Its frequency is going to be modulated by the magnetic field that the magnetic moments are creating here. And then the signal is going to come back out here, get amplified, down converted, and goes into a computer for digitizing the output. Okay, I'm going to go into details into this in the next lesson. Okay? So if anyone has questions, they can ask now. If not, you can log out.